Hello everyone. In this video, we will learn to define what is meant by empirical and molecular formulas, to calculate the empirical and molecular formulas from masses, molar masses, elemental analysis data, and combustion analysis data. We have already discussed what a molecular formula is. The molecular formula shows the type of each element and the actual number of atoms of each element present in a molecule of the compound. And the empirical formula shows the simplest whole number ratio of various elements in a compound. Let us discuss few examples. Example 1. Hydrogen peroxide. The molecular formula of hydrogen peroxide is H2O2. The molecular formula tells us that the hydrogen peroxide has two different types of atoms, that is, hydrogens and oxygens. In addition, it also tells us that there are two hydrogens and two oxygens in a hydrogen peroxide molecule. Now let's calculate the empirical formula for this molecule. The ratio of hydrogens to oxygens in this molecule is 2:2. To reduce this ratio to the simplest whole number, we divide all the numbers with the smallest one. This reduces the ratio into 1:1. Therefore, the empirical formula is H1O1 or simply HO. Example 2. Glucose. The molecular formula of glucose is C6H12O6. The molecular formula tells us that each molecule of glucose contains 6 carbons, 12 hydrogens, and 6 oxygens. Now let us calculate the empirical formula for this molecule. The ratio of carbons to hydrogens to oxygens is 6:12:6. To reduce this to the simplest ratio, we divide all the numbers with the smallest one. In this case, it is 6, which reduces the ratio into 1:2:1. Therefore, the empirical formula is CH2O. Example 3. Water. The molecular formula of water is H2O, that is, 2 hydrogens and 1 oxygen per molecule. Now let us calculate the empirical formula for this molecule. The ratio of hydrogens to oxygens is 2:1. And this is the simplest ratio we can get. Therefore, the empirical formula can be written as H2O. Note that for some compounds, the molecular formula cannot be reduced anymore. Then, the empirical formula is the same as molecular formula for those compounds. Different molecules may have same empirical formula. An example is a class of compounds in organic chemistry called alkenes. Alkenes have same empirical formula but different molecular formula. Example: C3H6, C4H8, C5H10. All of them have an empirical formula of CH2. The molecular formula is a whole number multiple of the empirical formula. For example, if we want to get the molecular formula of hydrogen peroxide from its empirical formula, we need to multiply the empirical formula by a whole number, that is 2. Similarly, for glucose, if we multiply the empirical formula CH2O with a whole number, that is 6, we get the molecular formula of glucose. The molar mass of a compound is a whole number multiple of the empirical formula mass. We know how to calculate the molar mass of a compound, which is by adding the molar masses of all the atoms in a molecular formula. Similarly, if we add the molar masses of all the atoms in an empirical formula, we get empirical formula mass. And the molar mass of a compound is a whole number multiple of the empirical formula mass. For hydrogen peroxide, the molar mass is 34 and the empirical formula mass is 17 and the multiple is 2. Similarly, for glucose, the molar mass is 180 and the empirical formula mass is 30 and the multiple is 6. Note that the whole number multiple that connects the empirical formula and the molecular formula is the same as the one that connects the empirical formula mass to the molar mass. Let us do an example. Calculate the molecular formula of a compound with empirical formula NO2 and a molar mass of 92.01 grams per mole. We know that the whole number multiple that connects the empirical formula and the molecular formula is the same as the one that connects the empirical formula mass and the molar mass. The molar mass of the compound is given as 92.01 and the empirical formula is given as NO2. If we know the empirical formula, we can calculate its empirical formula mass. Empirical formula has 1 mole of nitrogen and 2 moles of oxygen. 1 mole of nitrogen weighs 14.01 grams and 2 moles of oxygen weighs 2 times 16.00 grams. If we do the math, we get 46.01 grams. Now we know the molar mass and the empirical formula mass. To get the whole number, we divide the molar mass with empirical formula mass, that is 92 divided by 46. So the whole number multiple is 2. Therefore, the molecular formula is equals to 2 times the empirical formula, that is 2 times NO2, and the molecular formula is N2O4. One of the first things chemists do when they synthesize a new molecule is to determine its molecular formula. In the next few slides, we will learn how to determine the molecular formula of an unknown compound based on some experimental results. We can break down the process into 2 steps. 1. Determine the empirical formula from the masses or mass percent values of various elements present in a compound. 2. Determine the molecular formula from the molar mass of the compound and the empirical formula. Chemists perform various experiments to determine the masses or mass percent values of various elements and the molar mass of a compound. We will discuss some of these experiments later in this video. Let us take a look at this example where we convert masses of various elements into an empirical formula. A 45 gram sample of an ionic compound is found to contain 8.46 grams of sodium, 13.05 grams of chlorine, and 23.49 grams of oxygen. What is the empirical formula of this compound? We learned that the empirical formula shows the simplest whole number ratio of various elements in a compound. To know the ratio of various atoms in this ionic compound, we need to know the number of moles of various atoms in this compound. Is there any way to determine the number of moles of each element given the mass of each element in grams? We have learned how to interconvert between the mass and the moles using the molar mass as the conversion factor. Let us now convert the masses of each element into moles of each element. We start with 8.46 grams of sodium and we need the number of moles of sodium. So we are going to multiply this with a conversion factor that cancels the grams of sodium and introduces moles of sodium. And the conversion factor is 1 mole of sodium per 22.99 grams of sodium. Grams of sodium gets cancelled, and if we do the math, we get 0.37 moles of sodium. Next, we do chlorine. We start with 13.05 grams of chlorine and we multiply this with a conversion factor which has grams of chlorine in the denominator and moles of chlorine in the numerator. And the conversion factor is 1 mole of chlorine for 35.45 grams of chlorine. The grams of chlorine gets cancelled and we get 0.37 moles of chlorine. Next, we do it for oxygen. We start with 23.49 grams of oxygen, multiply this with a conversion factor that has grams of oxygen in the denominator and moles of oxygen in the numerator, that is 1 mole of oxygen per 16.00 grams of oxygen. Grams of oxygen gets cancelled and we get 1.47 moles of oxygen. So, in 45 gram sample of ionic compound, we have 0.37 moles of sodium, 0.37 moles of chlorine, and 1.47 moles of oxygen. Next, we need to get the simplest whole number ratio of these elements. In order to do that, I am going to divide each of these numbers with the smallest of the number, which is 0.37 moles. We get the ratio of sodium to chlorine to oxygen as 1 to 1 to 4. Therefore, the empirical formula of this ionic compound is Na1Cl1O4. The next example involves both the steps, that is, convert mass percentage into empirical formula and empirical formula into molecular formula. Ibuprofen, a common headache remedy we use, contains 75.7% carbon, 8.80% hydrogen, and 15.5% oxygen. Determine the molecular formula if the molar mass of ibuprofen is 206 grams per mole. In the previous problem, we converted masses of various elements into the empirical formula. In this problem, we have mass percentages of various elements and we need to convert that into empirical formula. This is very similar to the last problem, but it has one small additional step, which is to convert the mass percentage into masses. What I'm going to do is assume I have 100 grams of ibuprofen. And since the mass percentage values of various elements are given, we can say that this 100 gram sample contains 75.7 grams of carbon, 8.80 grams of hydrogen, and 15.5 grams of oxygen. Now we know the masses of various elements present in the sample. Pause the video here and convert these masses into empirical formula. First, we need to convert the masses of various elements into moles of various elements using molar mass of the atoms as the conversion factor. We have 75.7 grams of carbon and we need moles of carbon. So we need to multiply this with a conversion factor that cancels the grams of carbon and introduces the moles of carbon. That is 1 mole of carbon per 12.01 grams of carbon. Grams of carbon gets cancelled and we get 6.30 moles of carbon. Next, for hydrogen, we have 8.80 grams of hydrogen and we need to convert that into moles of hydrogen. We need to multiply this with a conversion factor that cancels the grams and introduces the moles, which is 1 mole per 1.008 grams. Grams of hydrogen gets cancelled. We get 8.73 moles of hydrogen. Next, we do the same thing for oxygen. We start with 15.5 grams of oxygen. We need to convert this into moles of oxygen. Therefore, multiply this with a conversion factor which cancels the grams and introduces the moles. That is 1 mole per 16.00 grams of oxygen. If we do the math, we get 0.96875 moles. So, in 100 grams of ibuprofen, we have 6.30 moles of carbon, 8.73 moles of hydrogen, and 0.97 moles of oxygen. To get the simplest ratio, we divide all these numbers with the smallest number, which is 0.97 moles. If we do that, we get the ratio of carbons to hydrogens to oxygens as 6.5 to 9 to 1. To convert this into a whole number, what I am going to do is multiply all these numbers with 2. So the ratio of carbons to hydrogens to oxygens is now 13 is to 18 is to 2. Therefore, the empirical formula is C13H18O2. The third step is to convert the empirical formula into the molecular formula using the molar mass of ibuprofen that is given. We have already done this type of problem, so pause the video here and try to answer this question. We know that to convert the empirical formula into the molecular formula, we need to multiply the empirical formula with a whole number multiple. And we can get the whole number multiple by dividing the molar mass of ibuprofen with the empirical formula mass. We already know the empirical formula, so we can calculate the empirical formula mass. The empirical formula of ibuprofen is C13H18O2, which means it has 13 moles of carbon, 18 moles of hydrogen, and 2 moles of oxygen. That is 13 times 12.01 grams of carbon, 18 times 1.008 grams of hydrogen, and 2 times 16.00 grams of oxygen. If we do the math, we get 206.27 grams. As we can see, the molar mass is the same as the empirical formula mass. That means the whole number multiple is 1 and the empirical formula is the same as molecular formula. Therefore, the molecular formula of ibuprofen is C13H18O2. One of the experiments that chemists use to determine the masses of individual elements in a compound is called combustion analysis. We take a small sample of the unknown compound, containing elements such as carbon, hydrogen, and others, and combust it in presence of excess oxygen. Upon combustion, all the carbon in the unknown compound is converted into carbon dioxide and hydrogen is converted into water. The products of this combustion reaction are then passed into a container with a water absorber in it, which absorbs all the water from the mixture of products. Therefore, the mass of the water absorber increases, and the leftover products are passed through a container with a carbon dioxide absorber, which absorbs all the carbon dioxide from the mixture of products. That increases the mass of carbon dioxide absorber. The remaining of the products are collected in the third container or any other absorbers if required. The mass of the absorbers before and after the combustion is measured. The difference in mass of the water absorber before and after combustion gives us the amount of water produced in the combustion. Similarly, the difference in the mass of carbon dioxide absorber gives us the amount of carbon dioxide produced in this reaction. Using these numbers, we can back calculate the molecular formula of the compound. We have a representative data for such an experiment. Let us calculate the molecular formula. When a 1 gram sample of an organic compound with molar mass of 176.12 grams per mole is placed in a combustion chamber and burned, the following data are obtained. Mass of carbon dioxide absorber after combustion is 85.35 grams. Before combustion is 83.85 grams. Mass of water absorber after combustion is 37.96 grams and before combustion is 37.55 grams. What is the molecular formula of the unknown compound? As we discussed earlier, the first step is to determine the mass of carbon dioxide released and mass of water released during combustion. Mass of the carbon dioxide released is equal to mass of the absorber after combustion minus mass of the absorber before combustion, which is 85.35 grams minus 83.85 grams. We get 1.50 grams. Similarly, for water, it is 37.96 grams minus 37.55 grams is equals to 0.41 grams. The important point here is that all the carbon present inside 1.50 grams of carbon dioxide that is released must have come from the unknown compound. Similarly, all the hydrogens present in 0.41 grams of water released during the reaction must have come from the unknown compound. Now let us calculate the mass of carbon in 1.50 grams of carbon dioxide. The proportion of mass contributed by carbon towards the carbon dioxide is always a constant, and this can be calculated by using the molar mass. First, let us calculate the molar mass of carbon dioxide. 1 mole of carbon dioxide has 1 mole of carbon and 2 moles of oxygen. 1 mole of carbon weighs 12.01 grams and 2 moles of oxygen weighs 2 times 16.00 grams. And the molar mass is 44.01 grams. So we can say that in 44.01 grams of carbon dioxide, 12.01 grams is contributed by carbon. So this can be used as a conversion factor to convert grams of carbon dioxide into grams of carbon. So we have 1.50 grams of carbon dioxide and we need grams of carbon. So we need to multiply this with a conversion factor which has grams of carbon dioxide in the denominator and grams of carbon in the numerator. That is 12.01 grams of carbon per 44.01 grams of carbon dioxide. Grams of carbon dioxide gets cancelled and we get 0.409 grams of carbon. All this carbon must have come from the unknown compound. Let us now calculate the mass of hydrogen in 0.41 grams of water. We start with 0.41 grams of water and we want grams of hydrogen. We need to multiply this with a conversion factor in which we have grams of water in the denominator and grams of hydrogen in the numerator. That is 2.016 grams of hydrogen per 18.02 grams of water. You can get this number by calculating the molar mass. If we do the math, we get 0.046 grams of hydrogen. All this hydrogen must have come from the unknown compound. So we can say that in 1 gram of the unknown compound, 0.409 grams of carbon was there and 0.046 grams of hydrogen was there. Since the unknown compound was made of only 3 elements, that is carbon, hydrogen and oxygen, mass of the oxygen can be calculated by subtracting the mass of carbon and mass of hydrogen from the mass of unknown compound. That is 1.00 grams minus 0.409 grams minus 0.046 grams. We get 0.545 grams of oxygen. Now we have masses of all the elements present in the compound. From this point onwards, it is pretty much similar to what we have discussed in earlier problems. We convert the masses into moles and then we take the simplest ratio to get the empirical formula, and then we use the molar mass to calculate the multiple, and then we convert the empirical formula into the molecular formula. Let us do it step by step. Next, convert masses into moles. We start with 0.409 grams of carbon and we need moles of carbon. So I multiply this with a conversion factor that has moles on the top and grams of carbon on the bottom. That is 1 mole of carbon per 12.01 grams of carbon. Grams of carbon gets cancelled and we get 0.0341 moles of carbon. For hydrogen, we start with 0.046 grams of hydrogen and multiply that with a conversion factor which is 1 mole of hydrogen per 1.008 grams of hydrogen. Grams of hydrogen gets cancelled and we get 0.046 moles of hydrogen. Similarly, for oxygen, we start with 0.545 grams of oxygen times 1 mole of oxygen per 16.00 grams of oxygen. If we do the math, we get 0.0341 moles of oxygen. So the ratio of carbons to hydrogens to oxygens is 0.0341 is to 0.046 is to 0.0341. In order to get the simplest whole number ratio, I am going to divide all these numbers with the smallest one, which is 0.0341. So the ratios that I get are 1 to 1.3 to 1. To convert this into a whole number, I am going to multiply all these numbers with 3. So the final ratio is 3 is to 3.9 is to 3, which can be approximated as 3 to 4 to 3. Therefore, the empirical formula is C3H4O3. In the last step, we use the molar mass and the empirical formula to calculate the molecular formula. The molar mass is given as 176.12 grams per mole, and we can calculate the empirical formula mass as 88.06. Therefore, the whole number multiple is 2 and the molecular formula is C6H8O6.